Good morning, everybody. It's been a couple of weeks. You guys missed me last week because I was having some issues with moving and things that were somewhat unexpected. So this week I'm going to make up for it, and we're going to talk about both week 9 and week 10, the practice problems from both of those weeks. And I've extended the week 9 problems to be due this week so that way you can work on them as well. If you need more time or you have any questions as things pop up, as always, just email me. So in chapter 5, we talked about pressure. And recall that the pressure on an object is defined as the force per unit area, the force on the object divided by the area on which the force is acting. Pressure is measured in units of pascals, in which 1 pascal is just 1 Newton per meter squared. And so let's take a look at some of these examples. The smallest bone in the index finger of a 74 kilogram circus acrobat has a cross-sectional area of 0.45 centimeters squared and breaks under a pressure of 2 times 10 to the 8th pascals. That's what the PA is short for. Not sure what happened with that line there. So is it safe to balance his entire weight on that one finger? Well, we can figure that out by determining the pressure on the finger. And if it's greater than 2 times 10 to the 8th, well, his finger will break. So recall that the force is going to be the weight of the acrobat, his entire weight. And so that's M times G, which is 74 kilograms times 9.8 meters per second squared. And that gives us a force of 725.2 newtons. The area is given to us in centimeters squared. We want to convert that to meters squared. That might be the hardest part of this problem. When you convert squared variables, we have to use the conversion factor twice. There's 100 centimeters in 1 meter. But we're going to write it down twice so that we cancel out centimeters squared. And then those 2 centimeters cancel out with these 2 down here. And we get 0.45 divided by 100 twice, or divided by 10,000. And so you just get some zeros in front. Meters squared. Now we have units of newtons and meters squared. To find the pressure, we will just divide the two, 725.2. The force divided by the area, so 725.2 divided by 0.000045. And that gives us a pressure on the acrobat's finger of 161155555 pascals, newtons per meter squared, which is 1.61 times 10 to the 1, 2, 3, 4, 5, 6, 7 pascals. So less than the pressure that his finger can hold. And so it would be safe. The answer here would be yes. He could balance himself on his pinky. So let's try another example. And you guys, there may be some breaks in the video today where I have to separate these a couple of times because my kids are around in the background and they may interrupt me. So just be kind of aware of that. If it breaks up a little bit, I will pause and return and finish the problem. At the distance of the Earth from the Sun, the pressure exerted by the Sun is about 10 to the minus 5 pascals. So that's 1 times 10 to the minus 5. How much force does this pressure exert on a 10-meter squared array of solar cells when it's perpendicular to the direction of sunlight? Well, we know the pressure and we know the area. We just need to figure out the force. And so, if we know the pressure is equal to the force divided by the area, we can solve this and just solve for the force, which is just the pressure times the area. So 1 times 10 to the minus 5 pascals times 10 meters squared. That gives us a force of 1 times 10 to the minus 4 newtons. And so this is the force of the sun on that solar array or the satellite. Part B, we want to determine if we have the mass of the satellite at 360 kilograms, what acceleration does the force give it? Well, we know the force was 1 times 10 to the minus 4 newtons. Now we know the mass is 360 kilograms. Think back to Newton's second law. The acceleration is equal to the force divided by the mass. So 1 times 10 to the minus 4 newtons divided by 360 kilograms divided by 360 kilograms. And you get an acceleration of 2.78 times 10 to the minus 7 meters per second squared. Now, this doesn't seem like a large acceleration, but over time, that would push a satellite and cause it to move in a different direction. Right? So satellites and things like this have to account for the pressure of the sun pushing on them. Even if the acceleration is really, really small, over time, it'll be enough to move it. One thing that we didn't talk about much last week were changes of phase in matter. We talked about how much energy or how much heat it would require to increase the temperature of a material to a certain point, but we didn't talk about what happens when those materials change phase. In order for a material to change phase, you have to supply it with more heat, more energy, right? Basically to break up the bonds or to separate them some, right? You need to push the stuff apart so that it'll change phase from a solid to a liquid or a liquid to a gas. So the amount of heat that's needed varies based on the phase change, but also based on the substance itself, right? So you have to look these values up for the latent heat of vaporization and the latent heat of fusion for each substance that you're interested in. So the examples will use water, but there are plenty of other substances that you can do this with. The total heat transferred or the total heat needed or the total heat during the phase change is the sum of everything, right? So when it changes temperature and then when it changes phase. And so how much heat is given off when 5 kilograms of steam at 100 degrees Celsius condenses and cools to water at 28 degrees Celsius? So two things are happening here. First, we have a phase change from steam to water. So from a gas to a liquid. So we would use the latent heat of vaporization for water to calculate the heat required for this phase change. If you look this up, the latent heat of vaporization for water is 2,256 kilojoules per kilogram. So to find the energy required for the phase change, we're just going to multiply that value times the mass. And so we have 5 kilograms, 2,256 kilojoules per kilogram. And when we multiply that, our answer will be in kilojoules, and we'll have 11,280 kilojoules. So this is the energy that it would give off, or the heat that would be given off as it went from steam to water. Now, as water, it's still only at 100 degrees. We need it to cool to 28. And so, to find that heat, we're going to use the mass, or the formula that we used last week, mc times delta T. Okay, so the mass in this case is still 5 kilograms. The specific heat of water, we can use lots of different versions of this, okay, but it is 4,184 joules per kilogram per degree C. We can rewrite this just to make our values a little simpler as 4.184 kilojoules per kilogram degree C. Right, just so we're in the same units as our original value. So we multiply times 4.184, and then the change in the temperature is going from 100 to 28, so that should be 72 degrees. The heat given off here, we're just going to multiply these three values, 5 times 4,184, you should get, times 72, you should get 1,506.24 kilojoules. And so the total heat is just the sum of these two values. So the phase change plus the heat required to change the temperature. And we find the total heat to be, did I add the two up? Let me put this in the calculator real quick, you guys. $12,786.24 kilojoules. Notice that most of that heat comes from the phase change. Okay, let's try another one. We have a total of 807 kilojoules of heat, so that's our total. So now we're kind of doing this backwards. We're added to 2.5 kilograms of water at 26 degrees Celsius. If we heat the water up like this, how much of the water is converted to steam? Well, first, we have to heat the water to 100 degrees. So let's figure out how much energy we're going to lose doing that. And so the amount of energy required to heat 2.5 kilograms, remember we can use the same specific heat, 4.5 kilograms. Remember we can use the same specific heat, 4.184 kilojoules per kilogram degree C. That is a constant, is the specific heat of water. And now we're taking 26 degrees Celsius, we're heating it to 100 so that it'll then convert to steam after it gets up to 100 degrees. And so this should be 74. If we multiply these three, you'll find that the heat used to raise it to 100 degrees Celsius is going to be 774 kilojoules. So this goes from 26 degrees to 100. So now we have a pot full of water at 100 degrees Celsius. The rest of the energy, the remainder of what's left over, so 807, we're going to write an R with it because that's what's left over, 807 minus 774.04 32.96 kilojoules. That's what's left over after we've heated it all to 100 degrees. So how much of that energy will heat up the water? How much of that water that's there now at 100 degrees will be heated up and turned into steam when you add 33 essentially kilojoules to it? And so to figure that out, we're going to use the latent heat of vaporization again. We know we have 32.96 kilojoules. The mass is what we're looking for. We want to know how much turns to steam, and that latent heat of vaporization does not change. Kilojoules per kilogram. And so now we would just divide. Divide both sides by 2256. And we find that the mass in kilograms is 0.0146, or about 14.6 grams. I don't know what happened with the line there. So not that much of the water was turned into heat. I'm sorry, was turned into steam, but all of the water was heated up to 100 degrees. What always happens in this case is that you have to heat all of the water to 100 degrees before it'll start turning into steam. And then you have to continue to add heat to it in order to turn it into steam. When you boil a pot of water on the stove and it starts boiling, it's at 100 degrees Celsius. It doesn't get any hotter than that. As the water itself heats up, it turns to steam. A pot of boiling water will never be any hotter than 100 degrees Celsius, because every bit of heat that goes into it afterwards turns that water into steam. Okay, so that brings us to this week and talking about something totally different. Well, maybe not totally different, but electricity and where the idea of electricity comes about. And so there are plenty of videos where I discuss all of the different concepts that go into this. But I want to show you how you can solve some problems with these. And so to do that, I want to just briefly discuss the subatomic particles, the particles that make up an atom. Atoms make up everything. And there are three, right? The proton and the neutron, which reside in the nucleus of an atom. They have nearly the same mass, but different charges. And then you have an electron, which is way, way smaller in terms of mass, but it has a negative charge equal to the positive charge of a proton. We'll use some of these constants for some problems, and so I wanted to make sure I included these here. They're also just really helpful to know. A plastic ball has a charge of 5 times 10 to the minus 11 coulombs. And so what's strange about some of the letters we use a capital Q for heat, but we use a lowercase q to represent a charge. So a plastic ball has a charge of 5 times 10 to the minus 11 coulombs. Now I mentioned this in the other videos, but 1 coulomb of charge is a huge amount of charge. So you can have much, much smaller values than that most times. So even a charge of 5 times 10 to the minus 11 coulombs. Recall that if you have a positive charge on some object, like a ball, this likely means that it has lost electrons. If you have a negative charge, it means it has gained electrons. Electrons are generally the thing that moves between at least solid objects. Liquids can be a little different. You can have moving protons in liquids, moving positive ions. We'll likely discuss more of that later. For now, let's figure out how many electrons we would need to get this kind of charge. To do that, we would just divide by the charge of an electron, a single electron. And so to find the number of electrons, we're going to use the total charge divided by the charge of one electron. And so that's 5 times 10 to the minus 11 coulombs divided by 1.602 times 10 to the minus 19 coulombs. And that will tell us how many electrons we have in, or how many we've lost to give this ball its positive charge. And we find we get 0.0007008. Oh, sorry, I hit multiply instead of divide. Let me erase that. Let's try that one again. So 5 times 10 to the minus 11 divided by 1.602 times 10 to the minus 19. And we find the number of electrons 312,109,862, or 3.12 times 10 to the 8th electrons. So a lot. Okay. We're going to pause here before the next one so I can go check on my kids who are in the background right now. And we will pick back up in just a second.